This is an illustration of cosmological history, which includes a detailed account of the cosmological inflation period. We'll deep dive into this illustration momentarily, but we can summarize the history of the cosmos by outlining 14 key events. The 14th event is a general reference to the distant future and the 13th event refers to the present epoch. So, between the Big Bang and now, we've identified 12 key cosmological events. To begin with, we identify the start and end of the cosmological inflation period. You can see that cosmological inflation started at t equals 0, and finished by 2t phi rho, that is, when the universe was about 10 to the minus 23 seconds old. Our estimate is slightly longer than the standard model of cosmology, which estimates the cosmological inflationary period to have finished by approximately 10 to the minus 35 seconds. Let's now walk through the illustration. The first key event was the Big Bang and it occurred at T alpha. At this instant, the cosmological temperature was 0 Kelvin and the magnitude of the Hubble constant was approximately 10 to the 61 km per second per megaparsec. The second key event occurred at root 2 T alpha. This is when the cosmological constant transitioned from being positive to negative. At this instant, the cosmological constant and the dark energy density parameter equaled 0. The third key event was the instant when cosmological acceleration began, represented by T1. At this instant, the cosmic microwave background radiation was at its maximum value of 10 to the 31 Kelvin, and the Hubble constant decreased from its Big Bang magnitude of 10 to the 61 km per second per megaparsec, to 0, but only for an instant. The instant when the Hubble constant was 0, is the instant when cosmological acceleration began. By the time the universe was 10 to the minus 42 seconds old at T2, the Hubble constant had increased from 0 to approximately 10 to the 60 km per second per megaparsec. So, this means that for an instant in time, the universe stopped expanding, then started expanding again. Although it has stopped expanding, it was continuing to inflate. An analogy to the behavior of the Hubble constant I have just described, might be a ball thrown into the air. At the top of its travel, the ball's velocity is 0, but it continues to experience constant acceleration. Therefore, the velocity of the ball is analogous to the Hubble constant and our constant gravitational acceleration environment is analogous to the cosmological inflation environment. Now that we've looked at cosmological inflation in some detail, we're going to scrutinize the 8th, 9th and 10th events. These events relate to standard model of cosmology estimates for the commencement of cosmological acceleration. To cut a long story short, the standard model of cosmology is in conflict with itself and from this, we've identified what we have termed to be, the cosmic acceleration problem. Let's now do a deep dive into it. In this illustration, we see the dark energy density parameter plotted by the red curve, the pressureless matter parameter plotted by the blue curve, and the deceleration parameter plotted by the magenta curve. The particle data group estimate for the commencement of cosmological acceleration is represented by the red circle, the U.S. Department of Energy estimate is represented by the black circle, and the Fermilab estimate is represented by the magenta circle. The electrogravimetric construct is considerably more precise than the standard model of cosmology. Consequently, we may interpret standard model of cosmology estimates for the commencement of cosmological acceleration as the graphical intersection points identified by the red, black and magenta circles. Thus, within the electrogravimetric construct, the particle data group estimate of 7.7 billion years maps to 7.3 billion years, the U.S. Department of Energy estimate of 9 billion years maps to 8.5 billion years, and the Fermilab estimate of 10 billion years maps to 9.6 billion years. Therefore, according to the electrogravimetric construct, the particle data group solution actually denotes the cosmological instant when the dark energy density parameter equaled 0. Moreover, the U.S. Department of Energy solution actually denotes the cosmological instant when the dark energy density parameter equaled the deceleration parameter. In addition, the Fermilab solution actually denotes the cosmological instant when the deceleration parameter equaled 0. So what's the bottom line? Well, On the previous slide, it was identified that the third key event was the instant when cosmological acceleration began, represented by T1. At this instant, the cosmic microwave background radiation was at its maximum value of 10 to the 31 Kelvin, and the Hubble constant decreased from its Big Bang magnitude of 10 to the 61 km per second per megaparsec, to 0, but only for an instant. The instant when the Hubble constant was 0, is the instant when cosmological acceleration began. However, since the standard model of cosmology lacks the accuracy of electrogravimetric predictions in the early moments of the universe, the standard model of cosmology relies upon the deceleration parameter to quantify cosmological acceleration. The problem with this is that the standard model of cosmology is insufficiently mature to precisely describe the complete history of the deceleration parameter, particularly in the early moments of the universe. Nor does the standard model of cosmology possess the required level of maturity to relate the deceleration parameter to the Hubble constant, unlike the electrogravimetric construct. Thus, we may utilize the electrogravimetric construct to compute the value of deceleration parameter in the early moments of the universe. When we do this, we find that the deceleration parameter transition from negative to positive at approximately T1, as defined on the previous slide. This reinforces the claim regarding the commencement of cosmological acceleration, asserted previously. At this juncture, we will reiterate that the standard model of cosmology does not relate Hubble constant to deceleration parameter over the full lifetime of the universe, as does the electrogravimetric construct. Having said this, we must acknowledge that the Fermilab estimate for the commencement of cosmological acceleration is correct in relation to the deceleration parameter, but incomplete. A more accurate description is that the Fermilab estimate is the correct value of the second instance of cosmological acceleration, based upon deceleration parameter. However, in relation to the Hubble constant, the Fermilab estimate for the commencement of cosmological acceleration is incorrect. So, what does all this mean? Well, it means that the universe has undergone two instances of cosmological acceleration. The first instance occurred immediately after the Big Bang, whilst the second instance occurred at a cosmological age of approximately 9.6 billion years. Thus, the particle data group and U.S. Department of Energy estimates are evidence of cosmological events, but not cosmological acceleration. Hence, the cosmological acceleration problem, which we have identified. Please note that all of the information required to replicate the results communicated in this video presentation appear on screen. Please take the time to study the information provided.